Hello, dear students. Today, we're delving into the intriguing world of voltaic cells and their behavior with respect to reactant concentrations. Imagine constructing a voltaic cell using reactants and products in their standard states. What happens to the concentrations of these reactants as the cell operates? Buckle up as we explore the changes that take place during the operation of a voltaic cell. Alright, students, let's dive into the specifics of how changes can impact the electromotive force, EMF, of a voltaic cell. Our voltaic cell involves the reaction aluminum, solid, plus 3 silver ions in aqueous solution, giving us aluminum ions in solution and 3 solid silver atoms. Keep in mind that EMF represents the cell's electrical potential. So, understanding how different changes affect it is crucial. Now, let's explore the effects of different changes on the EMF of our voltaic cell. Today, we're tackling the effect of dilution on our voltaic cell. Imagine adding water to the anode half cell, thus diluting the solution. How does this change influence the reactant concentrations and, consequently, the EMF of the cell? Let's explore this scenario in detail. Now, students, let's discuss the fascinating impact of electrode size on our voltaic cell. If we increase the size of the aluminum electrode, how does this decision affect the reactant concentrations and, consequently, the cell's EMF? Dive with me into the intricacies of electrode size and its connection to the flow of electric current. Time to uncover the outcomes of introducing AgNO to our voltaic cell's cathode half cell. By doing so, we're adding more Ag+ ions, while keeping the concentration constant. How does this alteration influence the reactant concentrations and, in turn, the EMF of the cell? Join me as we unravel the effects of this change. Lastly, students, let's explore the consequences of adding HCl to our AgNO solution in the cathode half cell. This leads to the precipitation of Ag+ ions as silver 1 chloride. What do these changes mean for the reactant concentrations, solubility, and EMF of our voltaic cell? Join me as we wrap up our journey through the effects of various alterations on the cell's behavior. And there we have it, students. We've explored the dynamic world of voltaic cells and how reactant concentration changes can influence their behavior. From dilution to electrode size and solution additions, each alteration holds its unique impact on the cell's EMF. Remember, as you delve into the world of electrochemistry, these factors play a crucial role in shaping the outcomes. Keep asking questions, keep exploring, and keep embracing the wonders of science. Hello, everyone. Today, we're diving into the world of voltaic cells, which are devices that convert chemical energy into electrical energy. In these cells, we have 2 half reactions occurring at different electrodes. Now, before we proceed, let's understand the key terms. Cathode is the electrode where reduction occurs, and anode is where oxidation takes place. Let's move on and explore the specific example you've mentioned. Alright, let's delve into the specifics of the half reaction involved. Silver 1 chloride S plus E turns into Ag S plus ClAq. In one half cell, we have a Cl concentration of 0.0150 m. And in the other half cell, it's 2.55 m. Now, which electrode do you think will be the cathode, where reduction takes place? And which will be the anode, where oxidation happens? Take a moment to think about it. Great job! Now, pay attention. The cathode will be the electrode with the lower chloride concentration. Why, you ask? Well, because a lower chloride concentration favors reduction, and the cathode is where reduction occurs. And that's not all. The cathode attracts positive ions or cations. So, in this case, the cathode is the half cell with the chloride concentration of 0.0150 m. Let's move on to the standard EMF of the cell. The standard EMF, E cell, is the difference between the standard reduction potentials of the cathode and anode. E degree cell equals E degree cathode minus E degree anode. This value is a measure of the cell's potential to generate electricity. Now, when it comes to the cell EMF in this specific scenario, keep in mind that concentrations play a role in altering the cell EMF from its standard value. Let's crunch some numbers. We can calculate the cell EMF using the Nernst equation. E cell equals E naught cell minus open parenthesis 0.0592 over n close parenthesis times log Q, where Q is the reaction quotient based on concentrations. This equation allows us to factor in the impact of concentrations on the cell EMF. Now, let's move on to predict how the Cl- concentration will change as the cell operates. Time to apply Le Chatelier principle. As the cell operates, changes in concentrations occur at the electrodes. At the anode, oxidation takes place, and Cl- ions are released into the solution, causing the Cl- concentration to decrease. At the cathode, reduction occurs, and Cl- ions are consumed, leading to an increase in the Cl- concentration. This dynamic interplay is a fascinating aspect of voltaic cells. Before we wrap up, let's quickly recap what we've covered today. We started by understanding the roles of the cathode and anode in voltaic cells. Then, we delved into calculating both the standard and cell EMF, considering the impact of concentrations on the latter. Finally, we explored how concentrations change at the electrodes during cell operation. This journey into voltaic cells and electrode reactions offers us a fascinating glimpse into the intricate world of electrochemistry. Welcome back, dear students. Today, we're delving into the world of batteries and their fascinating role in converting between electrical and chemical energies. Think about all the devices you use daily: laptop computers, cell phones, and even life-saving pacemakers. What powers these devices? Batteries do. In fact, batteries are indispensable for providing the electricity these devices need to function. But the story doesn't end there. The world of batteries is evolving rapidly, with intensive research aimed at creating new and improved battery technologies. Why, you ask? Well, think about electric vehicles, the storage of solar energy, and power tools. These areas require batteries that are lighter, charge more quickly, deliver greater power, and have longer lifetimes. The driving force behind these advancements lies in the fascinating oxidation-reduction reactions that power batteries. By the end of our exploration today, you'll be able to identify the key components of common batteries and understand their pivotal role in energy conversion. That concludes our introduction for today. Let's dive right in. Hello again, students. Today, we're delving into the captivating realm of batteries and their remarkable power generation abilities. Imagine having a portable source of energy at your fingertips. That's precisely what a battery is, a self-contained electrochemical power source. It consists of units called voltaic cells, which work together to produce the energy we need for various devices. Think of those 1.5 volts batteries that power your torches and electronic gadgets. Surprisingly, these are single voltaic cells. However, if we require more power, we can achieve greater voltages by combining multiple cells. For instance, the 12V batteries found in vehicles are created by connecting multiple cells. This is done in series, where the cathode of one cell is linked to the anode of another. The remarkable result? The battery generates a total voltage equal to the sum of the individual cell voltages. This concept is illustrated in Figure 20.18. Remember, battery electrodes are marked according to a convention: plus for cathode and minus for anode, as seen in Figure 20.6. So, the next time you use a battery-powered device, you'll have a deeper understanding of the science behind it. Welcome, dear students, to a riveting discussion on voltaic cells and the fascinating realm of battery performance. Today, we're delving into the ingenious world of commercial batteries and the complexities that determine their characteristics. Voltaic cells, which harness spontaneous redox reactions, serve as the foundation for batteries. However, creating batteries with specific performance traits requires remarkable ingenuity and understanding. Now, let's take a closer look at how the substances oxidized at the anode and reduced at the cathode play a crucial role in establishing the voltage of the battery. Additionally, the usable lifespan of a battery is intricately linked to the quantities of these substances carefully packaged within it. To visualize this, imagine a barrier similar to the porous barrier depicted in Figure 20.6, separating the anode and cathode half cells. This barrier plays a pivotal role in battery functionality. As we continue, keep in mind that different applications call for batteries with distinct properties. Consider a car battery, for instance. It must have the capability to deliver a robust electrical current for a brief period. In contrast, a battery powering a heart pacemaker needs to be compact and provide a consistent low current over an extended time. Now, let's explore the concepts of primary and secondary cells. Primary cells can't be recharged and must be discarded or recycled once their voltage depletes to zero. On the other hand, secondary cells can be recharged externally after their voltage diminishes. As we delve deeper, students, let's explore the intricate art of tailoring batteries to meet the unique demands of diverse applications. Batteries are not one size fits all. They must be designed with specific traits for particular uses. Consider the battery required to start a car. It's designed to deliver a high electrical current rapidly, allowing the engine to roar to life. However, this burst of power is only needed for a short period. Contrast this with the battery powering a heart pacemaker. In this scenario, the battery must deliver a steady, low current over an extended time to ensure the pacemaker functions flawlessly. Our journey into battery engineering wouldn't be complete without discussing primary and secondary cells. Primary cells, such as those in regular household batteries, are unable to be recharged. Once their voltage drops to zero, they must be responsibly discarded or recycled. Secondary cells, however, offer a more sustainable solution. These cells can be recharged from an external power source after their voltage has declined, giving them a second lease on life. This flexibility in recharging makes secondary cells an environmentally friendly option. Now, my inquisitive learners, let's take a plunge into the captivating realm of battery chemistry. The performance of batteries is profoundly influenced by intricate chemical reactions taking place within them. These reactions are driven by redox processes, reduction and oxidation, critical for generating the energy that powers our devices. To truly grasp battery functionality, we need to delve into the world of electrochemical processes. Gaining an understanding of how electrons flow, ions migrate, and chemical transformations occur is crucial to unraveling the mysteries of battery operation. Consider that all energy in batteries, whether primary or secondary, is rooted in chemical reactions. These reactions result from the shifting of electrons and the rearrangement of atoms. It's worth noting that all forms of energy can be categorized as either kinetic or potential energy. When it comes to batteries, the energy generated from chemical reactions primarily involves changes in potential energy. This energy originates from the intricate electrostatic interactions unfolding at the atomic level. So, remember, every time you power up a device, you're tapping into the remarkable world of chemical reactions and energy conversion. As we continue our exploration, students, let's dive even deeper into the concept of battery potential and its broader implications. When we talk about battery potential, we're essentially discussing the energy stored within a battery. This energy is derived from the intricate dance of chemical reactions, which involve the transfer of electrons and the rearrangement of atoms. Remember that energy can exist in different forms, potential and kinetic. In the realm of batteries, potential energy is closely tied to the interactions happening at the atomic level. When we harness energy from redox reactions, we're tapping into this potential energy reservoir. It's the conversion of this stored energy that powers our devices, from the smallest gadgets to the most advanced technologies. So, whether it's a smartphone, a laptop, or even a cutting-edge electric vehicle, battery technology is at the heart of it all. As we wrap up our journey, keep in mind that our exploration of batteries has only scratched the surface of what's possible. The world of energy storage and conversion continues to evolve, presenting us with exciting opportunities to power the future. Hello, students. Today, we're delving into the world of lead-acid batteries, a vital part of automotive power systems. Our focus will be on understanding the structure and reactions within these batteries. Imagine a 12 volts lead-acid automotive battery that consists of 6 voltaic cells connected in series. Each cell produces 2 volts, contributing to the overall voltage. The cathode of each cell boasts lead dioxide, PbO2, packed on a lead grid, while the anode is made of lead. Both these electrodes are immersed in sulfuric acid. These components play a crucial role in the chemical reactions that take place during the battery's operation. Welcome back, everyone. Today, we're going to dive deeper into the fascinating world of chemical reactions within a lead-acid battery. During discharge, pay close attention to the cathode reaction. It involves the remarkable transformation of lead dioxide, represented chemically as PbO. Now, let's consider the key players in this reaction: hydrogen sulfate ions, denoted as HSO, and protons, symbolized as H. The magic happens as lead-2 oxide, HSO ions, and H come together and gracefully convert into lead sulfate, PbSO, and water, HO. But wait, that's not all. On the anode side, we have another captivating reaction. Imagine lead atoms, Pb, mingling with those HSO ions, resulting in the formation of lead sulfate, PbSO. In this process, they liberate protons, H, and charming little electrons, E. Are you still with me? Excellent. Now, my dear students, when we elegantly merge these reactions, we unveil the grand equation that governs the battery's mesmerizing operation. So, let's remember, PbO, HSO, H on one side, and Pb, HSO, protons, and electrons on the other, leading us to the captivating symphony of a lead-acid battery's chemistry. Keep up the fantastic work, and until next time, keep exploring the enchanting world of science. Great job, everyone! Now, let's tackle the concept of standard cell potential, a crucial factor in understanding battery performance. The standard cell potential, E-degree cell, is the measure of a battery's ability to produce electric potential under standard conditions. To calculate E-degree cell, we subtract the standard reduction potential of the anode, from the cathode. This difference gives us a value that represents the battery's overall potential. For our lead-acid battery, the calculation results in a standard cell potential of plus 2.05 volts. This positive value indicates that the battery is capable of generating a substantial electric potential. Fantastic progress, class! Let's wrap up our exploration of lead-acid batteries by discussing their practical applications and broader significance. These batteries play a crucial role in the automotive industry, providing the power needed to start engines and run various electrical systems. Beyond cars, they're used in backup power systems and uninterrupted power supply (UPS) setups to ensure continuous electricity in case of outages. While these batteries offer impressive utility, it's essential to address environmental concerns and promote recycling efforts due to the lead content. Despite challenges, lead-acid batteries remain versatile and widely used, showcasing their significance in our modern world. Your exceptional efforts have truly shone through, my diligent students. Let's take a moment to recap the key concepts we've explored today. We've journeyed through the structure of lead-acid batteries, the cathode and anode reactions, and the calculation of standard cell potential. We've also recognized the battery's vital role in the automotive industry and backup power solutions. Remember, as we harness the power of technology, we must also prioritize environmental responsibility and recycling. Your enthusiasm for learning is truly inspiring, and I can't wait to embark on our next exciting adventure together. Until then, keep your curiosity alive and your minds open to new horizons. Welcome back, students. Today, we're delving into the captivating world of batteries and their remarkable properties. Our focus now shifts to the lead-acid battery, where fascinating electrode reactions take place. The solid reaction products that form during these reactions have a special property: they adhere to the electrodes. Why is this significant, you ask? Well, it enables a fantastic phenomenon: the ability to reverse the electrode reactions during the charging process. Imagine the implications of this reversibility. This process allows the lead-acid battery to be recharged and used again, making it an essential component in various applications, from automobiles to backup power systems. Keep in mind the ingenious way science and engineering come together to bring us these practical solutions. Now, let's move forward to explore another captivating aspect of batteries. Hello, dear students. Today, we're about to embark on an electrifying journey through the world of battery technology. Our story starts with a battery type known as the nickel-cadmium, or NiCd, battery. These batteries possess attractive qualities but come with a major drawback: the use of cadmium as the anode material. Now, cadmium is toxic, which poses environmental and health challenges. As a result, NiCd batteries must be carefully recycled to avoid the harmful effects of cadmium. Due to its toxicity, the popularity of NiCd batteries has dwindled since their peak production in the early 2000s, which saw around 1.5 billion batteries being manufactured annually. Not only that, but cadmium's relatively high density adds unwanted weight to batteries, making them less ideal for portable devices and electric vehicles. These shortcomings have paved the way for the emergence of a newer technology: the nickel metal hydride, or NiM, battery. Let's dive into the intricacies of this evolution. Now, as we transition to the next chapter of battery technology, let's explore the incredible innovation known as the nickel metal hydride, or NiM, battery. This advancement was driven by the need to address the limitations of NiCd batteries. While the cathode reactions in NiM batteries share similarities with NiCd batteries, the magic lies in the anode reactions. In NiM batteries, the anode is composed of a metal alloy with Am5 stoichiometry. In simple terms, this alloy includes lanthanum, La, or a mixture of metals from the lanthanide series, and nickel alloyed with other transition metals. The charging process involves a fascinating transformation. At the anode, water is reduced to form hydroxide ions and hydrogen atoms. These hydrogen atoms are then absorbed into the Am5 alloy. As the battery operates and discharges, these absorbed hydrogen atoms are oxidized, and the resulting H+ ions combine with O ions to produce water once again. As we continue our exploration, let's take a closer look at the advantages that the nickel metal hydride batteries bring to the table. These batteries have been designed with a forward-thinking approach that considers environmental impact. By steering clear of toxic materials like cadmium, NiM batteries mitigate toxicity concerns and align with sustainable energy practices. Furthermore, the development of improved anode materials has led to a reduction in battery weight. This weight reduction is particularly noteworthy for devices that require portability, such as electronic gadgets and electric vehicles. The evolution of battery technology doesn't stop here, though. Researchers are continuously working to unlock even more advanced battery solutions that will power the future. Now, let's delve into the captivating world of energy conversion and the science that underpins battery technology. At the heart of battery operation lies a fascinating process called redox reactions, which involve the exchange of electrons between different elements. Anodes and cathodes play pivotal roles in this energy conversion. The anode is where oxidation occurs, releasing electrons, while the cathode experiences reduction, accepting those electrons. This flow of electrons is what generates the electrical energy we rely on. As we explore this intricate dance of reduction and oxidation, remember that these processes are the foundation of how batteries store and provide power to a myriad of devices and applications. Welcome, dear students, as we embark on an enlightening journey through the captivating realm of battery technology. Today, we delve into a crucial concept: the categorization of energy. You see, all forms of energy can be thoughtfully divided into two main types: kinetic and potential. Kinetic energy is the vibrant force linked to motion itself, while potential energy resides in the quietude of stored power. Now, my bright minds, when we turn our attention to batteries, we find ourselves immersed in the realm of altering potential energy. It's the chemical ballet, the redox reactions, that set the stage for these transformations. As electrons flow gracefully from one element to another, potential energy changes unfold. And where do these changes stem from, you ask? It's the electrostatic interactions that weave their magic at the atomic level. A truly remarkable phenomenon, my inquisitive minds, one that powers the very batteries propelling our modern world forward. So, let's embrace this knowledge and journey forth, as curious explorers of the science that shapes our world. As we wrap up our illuminating journey, let's take a moment to reflect on what we've learned. We began with the introduction of nickel-cadmium batteries, their limitations, and how those limitations paved the way for the emergence of nickel metal hydride batteries. This evolution showcased the synergy between environmental concerns and technological progress. Our exploration into redox reactions and energy conversion revealed the magic that powers batteries and enables them to provide electrical energy. And don't forget, all this energy is rooted in the intriguing dance of reduction and oxidation. With the ever-growing demand for cleaner and more efficient energy solutions, battery technology continues to advance, driven by a combination of innovation and necessity. As we conclude, I encourage each and every one of you to nurture your curiosity, explore the wonders of science and technology, and contribute to the remarkable journey toward a more sustainable and electrifying future. Hello again, students. Today, we're diving deep into the world of lithium-ion batteries. These batteries are the powerhouses behind our portable devices like cell phones and laptops. What makes them so special? Well, let's explore. Lithium-ion batteries have revolutionized the way we use technology due to their exceptional characteristics. Firstly, their specific energy density, which is the amount of energy stored per unit mass, is remarkable. This is made possible by the lightweight nature of lithium, giving Li-ion batteries a weight advantage over other types of batteries. Moreover, the standard reduction potential of Li+ is quite negative, leading to a higher voltage per cell compared to other batteries. For instance, a Li-ion battery based on the LiCo-O2 cathode can reach a maximum voltage of 3.7 volts per cell, which is almost 3 times higher than the voltage generated by nickel-cadmium and nickel-metal hydride batteries. This higher voltage results in a Li-ion battery being capable of delivering more power for its size, leading to a higher volumetric energy density, which is the amount of energy stored per unit volume. This combination of features has made Li-ion batteries the go-to choice for modern portable electronics. Let's move on to our next intriguing detail. Welcome back, dear students. Today, we're delving into the captivating realm of converting thermal energy into electrical energy. Get ready to uncover the magic behind this process. When we burn fuels, they release thermal energy. This energy can be harnessed to produce steam, which is no ordinary steam, it's the force that drives a turbine. Picture a giant spinning wheel, the turbine, being propelled by the power of steam. This spinning motion, in turn, drives an electrical generator, and voila, we have electricity. Fascinating, isn't it? However, keep in mind that there's a catch. Only about 40% of the energy from combustion can be efficiently converted to electricity using this method. The rest is lost as heat. So, our challenge lies in finding more efficient ways to transform energy. Now, let's move forward with our exploration. Hello, eager minds. Today, we're venturing into the realm of voltaic cells and their potential to directly produce electricity from fuels. It's like a technological marvel straight out of science fiction. Imagine, instead of going through the process of burning fuels to create thermal energy and then converting it to electricity, we could use voltaic cells to directly yield electrical energy from chemical reactions. This concept is truly revolutionary. Voltaic cells operate based on a fundamental principle: the conversion of chemical energy into electrical energy. This presents an exciting possibility for a more efficient way to generate electricity. While the combustion to electricity conversion method we discussed earlier reaches a maximum efficiency of 40%. Voltaic cells have the potential to achieve greater efficiency. This means we can unlock more of the energy stored in fuels. Isn't that astonishing? Let's continue our journey of discovery. Greetings, inquisitive minds. Today, we're venturing into the captivating world of batteries and the incredible redox reactions they rely on. Prepare to be amazed as we uncover the hidden magic behind these power sources. Within batteries, a remarkable process takes place: redox reactions. These reactions involve the exchange of electrons between different substances. As a result of these electron transfers, chemical energy is converted directly into electrical energy. Isn't it astonishing how chemistry plays a pivotal role in providing us with power? These electrochemical processes occur between the anode and the cathode of a battery. The anode releases electrons, and the cathode receives them, producing an electric current that we can use for various applications. The energy transformation happening within batteries has transformed the way we live our lives, powering everything from smartphones to electric vehicles. And this is just one example of the incredible ways chemistry shapes our world. Prepare to be further amazed as we continue our exploration. Welcome back, my eager learners. Today, we're delving deeper into the enchanting concepts of kinetic and potential energy, as well as their profound connection to chemical reactions. Prepare to unlock a new layer of understanding about the world of energy around us. All forms of energy can be categorized into two main types: kinetic and potential. Kinetic energy is the energy of motion, while potential energy is stored energy that has the potential to do work. When it comes to chemical reactions, potential energy is the star of the show. Chemical interactions involve changes in potential energy, driven by the electrostatic interactions occurring at the atomic level. It's like a dance of charges and forces shaping the energy landscape. This intricate relationship between energy and chemical transformations forms the foundation of many natural processes and technological advancements. As we continue our journey, remember that understanding these concepts opens the door to unlocking the mysteries of the universe. Let's keep exploring. Welcome back, students. In today's lecture, we're delving into the remarkable technology behind lithium-ion batteries, a fundamental component of modern portable electronics. Our journey takes us into the world of ion movement within layered solids. Imagine the intricate dance of Li+ ions as they insert into and exit from specific layered materials. These batteries consist of two main components: the anode and the cathode. The anode, often composed of graphite, boasts layers of sp2 bonded carbon atoms, creating a structure that facilitates the movement of ions. On the other side, the cathode is crafted from a transition metal oxide with a similar layered structure. Specifically, lithium cobalt oxide, or LiCoO2, is a common choice. But how does it all come together? Let's explore further. As we venture deeper, let's uncover the captivating process of charging and discharging within a Li-ion battery. During the charging phase, cobalt ions within the cathode undergo oxidation, setting off a sequence of events. Simultaneously, Li+ ions migrate from the LiCoO2 cathode to the graphite anode, a movement that's essential for storing energy. Picture this as the battery absorbing energy for later use. On the flip side, when the battery is discharging to produce electricity, the Li+ ions move spontaneously from the graphite anode through the electrolyte to the cathode. This movement creates an avenue for electrons to flow through the external circuit, powering our devices. It's like witnessing a symphony of ions and electrons orchestrating energy transfer. Stay tuned as we unravel even more about the inner workings of these incredible energy storage systems. Now, let's shed light on a crucial player in this battery drama, the electrolyte. Think of it as the bridge that allows Li+ ions to journey from the anode to the cathode, and vice versa. The electrolyte, like a diligent conductor, ensures that these ions can traverse the distance smoothly, enabling efficient charge and discharge cycles. It's fascinating to consider how this seemingly simple component plays a pivotal role in the overall performance of a Li-ion battery. As we continue our exploration, you'll realize just how interconnected and intricate this energy storage technology truly is. Let's sum up our journey so far. A Li-ion battery is an intricate interplay of various components, each with a specific role to play. The anode, crafted from graphite, features layers of sp2 bonded carbon atoms, while the cathode consists of lithium cobalt oxide with its own layered structure. The electrolyte, our conductor, bridges the gap between these components, facilitating the movement of lithium ions during both charge and discharge cycles. As the cobalt ions in the cathode oxidize during charging, lithium ions migrate to the graphite anode. During discharging, the spontaneous migration of lithium ions allows electrons to flow, producing electricity for our devices. This controlled dance of ions and electrons results in efficient energy storage and release. Stay curious, for there's much more to uncover about the remarkable world of battery technology. Good day, students. Today, we're delving into the exciting realm of electric vehicles and the remarkable progress they've made over the past 2 decades. This growth has been fueled by a shared desire to reduce our reliance on fossil fuels and decrease emissions. Now, let's explore the different types of electric vehicles available in the market. Alright, students, let's take a closer look at the 2 main categories of electric vehicles: hybrid electric vehicles, HEVs, and fully electric vehicles, EVs. Hybrid electric vehicles can operate using both batteries and conventional combustion engines. On the other hand, fully electric vehicles are powered exclusively by batteries. Additionally, hybrid electric vehicles can be further divided into 2 subcategories based on their charging methods, which we'll explore. Now, let's delve deeper into hybrid electric vehicles, HEVs. These vehicles can be powered by either batteries, conventional combustion engines, or a combination of both. There are 2 distinct types of HEVs: plug-in hybrids and regular hybrids. Plug-in hybrids need to be charged through conventional outlets, while regular hybrids employ regenerative braking and the combustion engine to recharge their batteries. Null. As we continue our exploration of electric vehicles, let's take a closer look at an essential factor that has driven their development: battery technology. Batteries used in electric vehicles need to possess both high specific energy density, which reduces the weight of the car, and high volumetric energy density, which minimizes the space required for battery packs. The graph you see on the topic illustrates the energy densities of different rechargeable battery types. Welcome back, students. Today, we're delving into the world of fuel cell systems and their remarkable efficiency. Fuel cell systems are fascinating devices that involve a unique chemical reaction. Specifically, the reaction between hydrogen gas, H2, and oxygen gas, O2, leads to the formation of water, H2O. These cells exhibit a significant advantage over traditional internal combustion engines, boasting twice the efficiency. Imagine a process that can generate electricity while being twice as efficient. Now, let's explore the reactions that take place within these cells under acidic conditions. Alright, students, let's dig deeper into the reactions occurring within fuel cells under acidic conditions. The cathode reaction involves the combination of oxygen gas, O2, 4 hydrogen ions, H+, and 4 electrons, E, to produce 2 molecules of water, H2O. On the other hand, the anode reaction features the breakdown of 2 hydrogen molecules, H2, into 4 hydrogen ions, H+, and 4 electrons, E. When we balance these reactions, we arrive at the overall equation. This balanced equation represents the heart of the energy-producing process within fuel cells. Now, remember, we're just scratching the surface of this intricate topic. Great job following along, students. Let's continue our exploration by focusing on the key players in fuel cells: hydrogen gas, H2, and oxygen gas, O2. Hydrogen gas serves as the fuel, while oxygen gas is sourced from the surrounding air and acts as the oxidant. When these gases come together in the fuel cell, the chemical reactions we discussed earlier take place, generating energy. It's fascinating to think that the air around us can contribute to the energy production process. Keep in mind that these reactions result in the generation of approximately 1 volt of electrical potential. You're doing fantastic, students. Let's wrap up our discussion on fuel cell systems by touching on their efficiency and potential. Remember how we mentioned that fuel cell systems are twice as efficient as internal combustion engines? This remarkable efficiency holds great promise for the future of energy production. With cleaner energy generation and a wide range of applications, including transportation, we're looking at a potential game-changer in how we power our world. As we conclude our journey into fuel cells, keep in mind the role of innovation and its impact on shaping our energy landscape. Hello, dear students. In our quest to understand energy transformations, let's now focus on a concept that revolves around the efficient conversion of chemical energy into electrical energy. This process is particularly fascinating, as it involves a higher rate of energy conversion. We introduce you to a remarkable device called the voltaic cell, which plays a crucial role in this conversion. In cases where conventional fuels like hydrogen, H2, and methane, CH4, are employed, these cells are specifically referred to as fuel cells. It's important to note that fuel cells are distinct from batteries due to their operational differences. While batteries are self-contained energy systems, fuel cells rely on a continuous supply of fuel to sustain the generation of electricity. Imagine the implications of such technology for powering various applications. Now, let's delve deeper into the mechanics of fuel cells and their unique attributes. Hello again, eager minds. Today, we're delving into a remarkable application of energy storage within the context of electric vehicles. Our spotlight falls on nickel metal hydride batteries, which have found significant practical use in this realm. These batteries boast a noteworthy characteristic. Their energy density is approximately 3 times higher than certain other battery types. This remarkable trait led them to be the preferred choice for commercial hybrid vehicles, such as the renowned Toyota Prius. Can you imagine the engineering marvels that have gone into developing these batteries? Let's move forward to unravel more secrets of energy storage and its role in driving innovation. Null. Welcome back, inquisitive scholars. As we explore the landscape of battery technologies, we're confronted with the dynamic nature of progress. Our focus now shifts to the transition from nickel metal hydride (NiM) batteries to a more recent player on the stage, lithium-ion (Li-ion) batteries. While NiM batteries made significant strides and earned their place in the world of hybrid vehicles, Li-ion batteries emerged with even more promise. These batteries are celebrated for their higher energy density and lighter weight. This advancement opened doors to increased efficiency and range for electric vehicles. It's no surprise that Li-ion batteries have garnered wider adoption in modern electric vehicles. Stay with us as we uncover the intricacies of these energy storage marvels. Hello again, bright minds. Let's continue our exploration of energy storage solutions, this time focusing on a pivotal player in the electric vehicle world: lithium-ion batteries. These batteries have risen to prominence as the dominant choice for electric vehicles. Why, you ask? Well, they excel in efficiently storing energy, translating into longer driving ranges and enhanced performance. But, like any technological marvel, there are challenges to address. Safety concerns related to overheating and resource limitations associated with the materials used in Li-ion batteries keep researchers and engineers busy as they work toward even safer and more sustainable solutions. As we wrap up our journey today, remember that the evolution of battery technologies is an ongoing saga of innovation and adaptation. Good day, students. Today, we're delving into the intriguing realm of fuel cells and exploring a specific type known as the hydrogen PEM fuel cell. Fuel cells are often named based on the fuel or electrolyte they use. In this case, PEM stands for either proton exchange membrane or polymer electrolyte membrane. Now, pay close attention to the structure of this fuel cell. The anode and cathode are separated by a specialized membrane, which is permeable to protons but not to electrons. Think of this membrane as a sort of salt bridge, facilitating the movement of charged particles. The electrodes, typically made from graphite, play a pivotal role in the cell's functioning. But here's where it gets interesting: the hydrogen PEM cell operates at a temperature of around 80 degrees Celsius. This is crucial because at lower temperatures, the electrochemical reactions would be sluggish. To counter this, tiny islands of platinum are strategically placed on each electrode to serve as catalysts. These catalysts speed up the reactions, making the cell more efficient. However, there's a catch. The cost and limited availability of platinum present challenges that hinder broader adoption of hydrogen PEM fuel cells. Let's proceed to the next topic for a deeper look. Hello again, students. Now, let's venture deeper into the intriguing realm of power generation, specifically through fuel cell technology. Picture this. In order to propel a vehicle, we need more than just one fuel cell. We need to assemble multiple cells into what we call a fuel cell stack. The amount of power this stack generates depends on factors such as the number and size of the fuel cells within the stack, as well as the surface area of the proton exchange membrane, PEM. Currently, researchers are heavily invested in refining electrolytes and catalysts, which play a crucial role in the efficiency of these fuel cells. They are also exploring innovative approaches by developing cells that can utilize alternative fuels like hydrocarbons and alcohols. These alternatives are more practical to manage and distribute compared to pure hydrogen gas. As we continue our journey, remember that fuel cells are a fascinating avenue of energy production, with their potential to revolutionize transportation and energy systems alike. Welcome back, curious minds. Today, let's delve further into the heart of fuel cell technology and explore some of the crucial elements that make it all work. Electrolytes and catalysts are the real MVPs here. Electrolytes facilitate the movement of ions between the anode and cathode, allowing the fuel cell to generate electricity. Catalysts, on the other hand, speed up the reactions at these electrodes, enhancing overall efficiency. Researchers are hard at work to make electrolytes and catalysts even better, aiming to boost the performance and longevity of fuel cells. Their efforts contribute to the ongoing advancement of this technology. Additionally, as we've mentioned before, the exploration of fuels like hydrocarbons and alcohols is gaining momentum, offering potential solutions to some of the challenges associated with hydrogen gas. Our journey through the world of energy continues, so let's keep our curiosity ignited. Hello once again, inquisitive learners. As we unravel the complexities of fuel cells, it's essential to think about their potential future. While hydrogen gas has long been a contender for fuel cell applications, there are challenges in handling and distributing it efficiently. That's where alternative fuels come into play. We've been touching on the exploration of hydrocarbons and alcohols as viable options. These fuels are easier to manage and distribute, making them attractive candidates for fuel cell systems. Imagine a world where a variety of vehicles, from cars to buses, are powered by these advanced fuel cells. This isn't just a dream. It's a potential reality that could reshape how we approach energy and transportation. So, as we wrap up this segment, keep your eyes on the horizon, because the energy landscape is evolving, and we're right here to witness its transformation. Welcome back, eager learners. Our exploration of fuel cells wouldn't be complete without considering their impact on the bigger picture of sustainability. Fuel cells are not just about power generation. They're about crafting a cleaner and greener future. By using fuels that are easier to handle and emit fewer pollutants, fuel cells contribute to the reduction of harmful emissions and environmental impact. The potential to integrate fuel cells into diverse sectors, from transportation to stationary power generation, opens up new avenues for sustainable energy solutions. Our journey through energy and chemical reactions is a testament to human ingenuity, dedication, and the unending pursuit of innovation. As we conclude our time together, remember that the world of science and discovery is always evolving, and you, the future generation, are at the forefront of driving positive change. Keep exploring, keep learning, and keep pushing the boundaries of knowledge. Hello, everyone. Today, we're delving into the intriguing world of batteries and their remarkable characteristics. To begin, let's clear up some distinctions between primary and secondary batteries. Primary batteries, also known as non-rechargeable batteries, cannot be recharged. In contrast, secondary batteries, or rechargeable batteries, can be recharged multiple times, making them more environmentally friendly. Now, take a look at the terminals of batteries. The one marked with a plus sign is where the oxidation reaction occurs. Remember, oxidation involves the loss of electrons, and this process happens at the positive terminal. Lastly, when it comes to batteries containing solid reactants, they exhibit an interesting feature. Throughout the discharge process, they maintain a constant voltage, which can be quite advantageous for certain applications. Keep these points in mind as we move forward in our exploration of energy and chemical reactions. Welcome back, students. Today, we're delving into the intriguing world of batteries and the chemistry behind their operation. Our focus now shifts to alkaline batteries. Imagine a scenario where 4.50 grams of Zn, zinc, is consumed during the discharge process at the anode of the battery. As we know, every battery involves half-cell reactions that occur at the anode and cathode. During this process, something fascinating happens at the cathode. Can you guess what it is? Well, MnO2, manganese dioxide, is being reduced. This reaction involves a transfer of electrons and the transformation of substances. Now, let's journey deeper into the details of these half-cell reactions. Hello again, dear students. Let's explore the world of electrical charge and its connection to the battery discharge process. We often measure electrical charge in coulombs, a unit that represents the flow of electrons. But how do we calculate the coulombs of charge transferred during the battery's operation? Well, it's linked to the number of electrons involved in the half-cell reactions. As electrons move from the anode to the cathode, electrical charge is transferred. So, when 4.50 grams of Zn is consumed at the anode, a specific number of coulombs of charge are transferred to manganese 4 oxide at the cathode. Let's continue to unravel the mysteries of batteries and their role in energy conversion. Greetings, eager minds. Our journey now leads us to the world of mercuric oxide dry cell batteries. These batteries find their purpose in devices like watches and cameras, where a consistent discharge voltage and extended lifespan are crucial. What makes these batteries special? They maintain a flat discharge voltage curve, ensuring steady performance over time. At the heart of these batteries lie fascinating half-cell reactions. One involves MgO, mercuric oxide being transformed into mercury at the cathode, accompanied by the presence of OH ions. The other reaction features zinc undergoing a transformation at the anode, leading to the creation of zinc oxide and releasing H2O water in the process. As we explore further, you'll realize the intricate dance of chemical reactions and energy exchange. Hello, dear students. Today, we're delving into the fascinating realm of electrochemical cells and the concept of standard reduction potentials. So, what are electrochemical cells? They're devices that convert chemical energy into electrical energy and vice versa. These cells consist of two half-cells, the cathode and the anode. The cathode is where reduction occurs, while the anode is where oxidation takes place. Now, let's talk about something called standard reduction potential, denoted as E°rad. This value helps us understand the tendency of a species to be reduced. But before we proceed, let's remember that a positive E°rad indicates a greater tendency for reduction. Keep this in mind as we venture into our next example. Welcome back, students. Now, let's get into some calculations. involving standard reduction potentials. We've got an overall cell potential of plus 1.35 volts, and a cathode E-degree red of plus 0.098 volts. Our task is to find the standard reduction potential for the anode reaction. This is where things get exciting. The relationship between E-degree red and the overall cell potential is like a puzzle piece that helps us unlock valuable information. You see, the overall cell potential is the difference between cathode E-degree red and anode E-degree red. The formula to use is overall cell potential equals cathode E-degree red minus anode E-degree red. We can rearrange this formula to solve for anode E-degree red. Let's embark on this journey of calculations together. Great work, students! Now, let's put our formula to the test and solve for the anode standard reduction potential. We'll rearrange the formula we discussed earlier. Anode E0 red equals cathode E0 red minus overall cell potential. Substituting the given values, which are cathode E0 red of plus 0.098 volts and overall cell potential of plus 1.35 volts, we'll work through the math to find the anode E0 red value. This value gives us insights into the anode reaction's tendency to undergo reduction. And remember, a higher positive value means a greater tendency for reduction. Let's uncover the anode potential and understand its significance. Hello again, inquisitive minds. Our journey continues, as we explore the factors that influence anode potential. The potential of the anode reaction might not always match our expectations, especially when the reaction occurs in an acidic environment. You see, the potential of the anode reaction is influenced by the reaction surroundings, like pH and concentration. In acidic conditions, the potential might differ due to the rate at which the reaction occurs. pH affects the availability of protons, which can speed up or slow down reactions. Concentration plays a role too. Higher concentrations of reactants can alter the potential. Temperature also comes into play, affecting the reaction kinetics. So, remember, the anode's potential isn't set in stone, it can change based on these various factors. Well done, my eager learners. Let's summarize our enlightening journey today. We've journeyed through electrochemical cells, delved into the concept of standard reduction potentials, and cracked the code to calculate anode potential. Keep in mind that our calculations assume standard conditions, and real-world scenarios can introduce complexities. Our journey doesn't end here. Understanding anode potential has real-world applications. From batteries to corrosion prevention, this knowledge is a gateway to technological advancements. So, don't stop here, keep exploring the world of electrochemistry, and uncover its boundless wonders. Hello, dear students. Today, we're embarking on a journey through electrochemical reactions and the fascinating realm of batteries. Our exploration begins with understanding cathode and anode half reactions. The cathode half reaction involves reduction, while the anode half reaction involves oxidation. Now, let's dive into your questions. Welcome back, students. Today, we're going to delve deeper into the fascinating world of cathode and anode half reactions. These reactions are key players in the realm of electrochemistry, and understanding them is fundamental to grasping the intricate mechanisms at play. Now, let's start by focusing on the cathode half reaction. This process is all about reduction, a process where electrons are eagerly gained, leading to the transformation of a chemical species into a new, reduced form. On the flip side, we have the anode half reaction. Here, the spotlight is on oxidation, a process in which electrons are relinquished, resulting in the alteration of the chemical species involved. These captivating half reactions aren't just theoretical concepts, they're the backbone of battery functionality. Think about it, they orchestrate the dance of electrons and ions, enabling the mesmerizing flow of electric current that powers our devices and vehicles. So, as we journey through the intricate landscapes of cathode and anode half reactions, remember to keep your scientific curiosity ignited. The more we comprehend these underlying principles, the brighter our understanding will shine. Great job, students! Let's put our knowledge to the test. In the case of a nickel-zinc battery, we can estimate its voltage based on the standard reduction potentials of Cd2+ and Zn2+. The difference in these potentials gives us a glimpse into the potential voltage output of the battery. This estimation helps us understand how different materials can influence the energy output of batteries. Excellent progress, students. Now, let's shift our focus to the specific energy density of batteries. When comparing nickel-zinc and nickel-cadmium batteries, we need to consider which one would have a higher or lower energy density. Factors like the types of reactions, materials used, and overall design play a crucial role in determining energy density. We'll explore how these factors contribute to the performance and applications of these batteries. Null. Hello again, bright minds. In our pursuit of knowledge, we now turn our attention to the lithium content within various electrode materials. One question prompts us to compare the lithium percentage in different materials. This information is vital as it has implications for battery performance. As we dig deeper, we find that some materials possess a higher lithium content than others. This difference has a direct impact on battery behavior. But does a higher lithium percentage always mean better performance? Let's explore this intriguing concept further. Greetings, eager learners. Our journey takes us into the realm of battery performance and its intricate relationship with lithium content. Here, we consider a crucial question. Why do batteries made with Lim-204 cathodes deliver less power on discharging? To answer this, we must investigate the connection between lithium migration and power output. As lithium migrates within electrode materials during charging and discharging cycles, it affects how efficiently the battery can deliver energy. Now, let's continue our quest for understanding. Hello again, curious minds. We're about to dive deeper into the specifics of lithium migration within battery cathodes. Specifically, we'll examine two cathode materials, LiCo02 and Lim-204. In one case, approximately 50% of lithium migrates from the cathode to the anode during charging. Now, the question arises, how much lithium would need to migrate out of a Lim-204 cathode to deliver the same amount of lithium to the graphite anode? Let's uncover the answer and gain insights into the fascinating world of battery chemistry. Welcome back, inquisitive learners. Today, we're embarking on a journey to distinguish between batteries and fuel cells. A battery stores energy within it and converts it into electrical energy. In contrast, a fuel cell generates electricity by harnessing an electrochemical reaction between a fuel and an oxidant. But here's an interesting twist to ponder. Can the fuel of a fuel cell be a solid substance? This thought-provoking question leads us into a discussion about the possibilities, advantages, and challenges of using solid fuels and fuel cells. Let's explore this avenue together. Hello, students. Today, we're going to delve into a fascinating topic, corrosion and its implications. Corrosion is a process you might have come across before, especially when it comes to the rusting of iron. This process carries significant economic consequences, particularly due to its impact on iron objects. When iron rusts, it actually increases in volume compared to the original iron. This can become a problem, as it can lead to the destruction of the structural integrity of iron-reinforced constructions. In fact, it's estimated that a significant portion of the iron produced annually in the United States, up to 20%, is used to replace items that have been discarded due to rust damage. Let's move on to the next topic to explore this topic further. Welcome to topic number 2, where we'll explore some of the challenges associated with controlling corrosion. One scenario where corrosion poses a significant challenge is in iron boats. These boats are often exposed to seawater, which acts as an excellent electrolyte, facilitating the corrosion process. What makes matters more complicated is that the site of corrosion is frequently hidden from view due to being underwater. As you can imagine, this makes inspecting and addressing corrosion quite difficult. So, how do we tackle this issue? Let's Move on to the next topic to learn about a method used to protect iron and prevent corrosion. Topic number 3 brings us to a practical solution for combating corrosion. Sacrificial anodes. One effective method of protecting iron surfaces from corrosion involves attaching a more active metal, often zinc, to the iron. This anode is sacrificial, meaning it corrodes preferentially over the iron. By doing so, it prevents the iron from undergoing significant corrosion. The benefit here is that sacrificial anodes are easier to inspect for electrochemical corrosion compared to inspecting the entire hull of a ship. This method is especially useful for iron boats that face the challenges of underwater corrosion. So, by employing sacrificial anodes, we can preserve the hull and structural integrity of ships. Let's proceed to the next topic to wrap up our exploration of this intriguing topic. Here we are at the last topic, wrapping up our discussion on corrosion. We've learned about the significant economic impact of corrosion, especially in scenarios like the rusting of iron. The increase in volume during rust formation can lead to the structural degradation of iron-reinforced constructions. Additionally, we explored the challenges posed by hidden corrosion sites underwater, particularly in iron boats. But fear not, we've also discussed a practical solution in the form of sacrificial anodes. By attaching a more active metal like zinc to iron surfaces, we can prevent extensive corrosion. Sacrificial anodes corrode preferentially, making inspection and maintenance easier. This method is particularly useful in maintaining the hulls of ships. And with that, we conclude our journey into the world of corrosion and its prevention. Thank you for joining me, and I look forward to our next exploration. Hello, students. In today's lesson, we're delving into a topic that highlights the challenges metals face in their environment. We'll be exploring corrosion of metals, undesirable redox reactions. So, let's start by understanding what corrosion is all about. Corrosion involves spontaneous redox reactions that occur when a metal interacts with substances in its surroundings, leading to the formation of unwanted compounds. This process can be quite destructive if left unchecked. We're going to uncover the factors that influence corrosion and learn how to prevent it effectively. Now, let's move on to our next topic to explore the factors and consequences of these reactions. Welcome back, students. Our journey through the world of corrosion continues. Today, we're diving into the factors that play a crucial role in the corrosion process. The environment has a significant impact on how metals react, and we'll be discussing these environmental factors. Additionally, we'll explore strategies that can be employed to prevent or inhibit corrosion, safeguarding the integrity of metals. Keep in mind that oxidation, a key player in these reactions, can sometimes lead to the formation of a protective oxide layer, which can act as a shield against further corrosion. Let's proceed to the next topic, where we'll delve deeper into the specifics of these corrosion reactions. Great to see you all engaged, students. Now, let's dive into the heart of oxidation and how it relates to metal protection. Imagine this. For most metals, oxidation is energetically favored in the presence of air at room temperature. However, don't despair. Oxidation can actually play a protective role. When certain metals undergo oxidation, they form a thin but crucial oxide layer on their surfaces. This layer acts as an insulating barrier, shielding the metal from further corrosion. So, remember, while oxidation may seem concerning, it can also be a natural defense mechanism. Shall we move on to the next part of our lesson? It's going to get even more intriguing. Hello once again, dear students. Today's adventure takes us deeper into the realm of chemical reactions involving metals. Our focus shifts to the intriguing phenomenon of oxidation and corrosion, particularly in the context of active metals. Let's consider aluminum as an example. Based on its standard reduction potential, we might anticipate aluminum metal to readily undergo oxidation. However, if you've ever noticed those aluminum soda cans scattered in the environment, you might be puzzled. Despite our expectations, aluminum experiences slow chemical corrosion. Why is that? Well, the answer lies in the exceptional stability brought about by the formation of a protective oxide coat. This coat, composed of a hydrated version of aluminium oxide, forms on the surface of aluminum. This oxide layer is incredibly clever, it doesn't allow oxygen or water to permeate through. As a result, the underlying metal remains shielded from further corrosion. This same principle of protection applies to metals like magnesium, which also develop protective oxide layers. Even metal alloys, such as stainless steel, join the protective oxide party. Isn't it fascinating how chemistry plays a role in preserving metals? Now, let's dive even deeper into the mechanics of these reactions. Hello, dear students. Today, we're delving into a fascinating topic: the corrosion of iron, commonly known as rusting. So, buckle up as we embark on this journey of understanding the intriguing processes behind rust formation. Welcome back. Let's dive deeper into the rusting process and explore the factors that contribute to its acceleration. Rusting requires both oxygen and water, which initiate the chemical reactions leading to corrosion. However, there are certain factors that can speed up this process, such as variations in pH levels, the presence of salts, contact with metals less prone to oxidation than iron, and even mechanical stress on the iron surface. Hello again, young minds. Now, let's unravel the science behind the corrosion process. Corrosion isn't just a random phenomenon, it involves structured chemical reactions. These reactions encompass oxidation and reduction processes. Here's where things get interesting. Metals, including iron, have the unique ability to conduct electricity. This means that electrons generated during corrosion can travel through the metal. They journey from the anode, where oxidation occurs, to the cathode, where reduction takes place. Imagine this process like a small electrical circuit within the metal. Great to have you back, students. Let's continue our exploration. Did you know that the electron flow during the corrosion of iron is quite similar to what happens in voltaic cells? Yes, those same voltaic cells you've heard about. The concept of standard reduction potentials comes into play here. In fact, the interaction between iron and oxygen is a prime example. Iron, in the form of Fe1S2, can be oxidized by molecular oxygen, O21. This connection between corrosion and electrochemical processes is truly captivating. Hello again, inquisitive minds. Let's wrap up our journey through the corrosion of iron. In this process, certain areas of the iron, often those with dents or strains, act as anodes. Here, iron undergoes oxidation and gets converted into Fe2+. The electrons produced during this oxidation travel through the metal. These electrons journey towards other regions of the iron surface, where the cathode is located. At the cathode, oxygen molecules are reduced, forming HuO. And just like that, we've witnessed the remarkable dance of chemical reactions and electron flow that lead to rusting. Welcome, students. Today, we're delving into an essential aspect of chemical reactions and their interaction with pH levels. Our focus lies on the reduction of oxygen, a process that requires the presence of H+ ions. Interestingly, altering the concentration of H+ ions by adjusting the pH value plays a significant role in determining the favorability of oxygen reduction. When the pH is increased, and the concentration of H+ ions decreases, the reduction of O2 becomes less favorable. This brings us to a fascinating observation related to corrosion. When iron comes into contact with a solution boasting a pH greater than 9, it doesn't corrode easily. Now, let's move forward to understand the intricate details of the reactions taking place. Hello again, dear students. Our journey continues into the captivating world of chemical reactions and their consequences. We're about to dive into the transformation of iron, so buckle up. At the anode, a noteworthy process takes place. Fe ions are formed. These Fe ions don't stop there. They undergo oxidation, turning into Fe ions. This leads us to a familiar term, rust. Yes, you heard it right. The hydrated iron, oxide, known as rust, is a product of this reaction. Just imagine the changes happening on a microscopic level that result in this visible transformation. Isn't chemistry fascinating? Let's proceed to our next intriguing concept. Greetings, curious minds. Our quest for knowledge wouldn't be complete without delving into the specifics of reactions themselves. Today, we're presenting you with the balanced equation that encapsulates the process of rust formation. This equation elegantly captures the interaction between the reactants, 4 Fe2 plus ions, oxygen, water, and XH2O molecules, and the resulting products, namely hydrated iron 3 oxide, iron 1 oxide 3, along with XH2O molecules and 8H plus ions. A balanced equation, like the one before us, is a powerful tool. It allows us to understand how reactants transform into products while conserving mass and charge. Let's unravel more insights as we proceed. Great to see you all engaged, students. Now, let's connect the dots between what we've learned and practical applications. Corrosion, as we know, can be detrimental, especially in contexts involving metals like iron. Here's where our knowledge of pH plays a crucial role. By controlling the pH of a solution, we can inhibit corrosion. Remember, a higher pH, meaning a more alkaline solution, can act as a protective barrier against corrosion. This preventive measure finds its applications in various scenarios, from industrial machinery to everyday objects. Imagine how understanding the principles of chemistry empowers us to protect and preserve our world. Let's wrap up with a summary of the key takeaways from our enlightening journey. Well done, dear students. We've journeyed through the intricacies of pH, oxidation, and corrosion. Let's quickly recap the key takeaways from our exploration. We learned how pH levels influence the reduction of oxygen and, consequently, the favorability of corrosion. The transformation of Fe2 plus ions into Fe3 plus ions at the anode leads to the formation of rust. Balanced equations give us a window into the magic of chemical transformations. And last but not least, we discovered how controlling pH can be an effective method to prevent corrosion and protect metals. As we conclude today's lesson, remember that the world of chemistry holds countless wonders waiting to be unraveled. Keep your curiosity alive, and keep exploring. Until next time. Hello again, dear students. Today, we're delving into an intriguing topic: hydrates and their connection with metal compounds. You see, when we obtain metal compounds from aqueous solutions, they often come with a companion water molecules. These compounds, aptly named hydrates, are fascinating examples of the interaction between substances. Let's take copper, 2-sulfate as our starting point. When it crystallizes from water, it brings along 5 moles of water for every mole of CuSO. This remarkable combination is symbolized by the formula CuSO5HO. Imagine water and the compound intertwined, forming a unique structure. But wait, there's more. Rust, which is iron 3 oxide, also comes in a hydrate form. However, its water content can vary, leading to a formula like FeOXHO, where X represents the variable amount of water of hydration. This variation adds another layer of complexity to our understanding. Now, let's journey further and explore the intricate world of these hydrates and their captivating properties. Welcome back, students. In today's session, we're delving into a rather interesting phenomenon known as corrosion. Corrosion occurs when metals react with their environment, particularly in the presence of oxygen and moisture. Now, let's focus on cathodic areas. These are regions with ample supplies of oxygen. You might have noticed this phenomenon in action when observing a shovel that's been left outside with wet dirt on its blade. Take a closer look, and you'll see that under the dirt, pitting has occurred. However, rust tends to form in places where oxygen is more readily available. This brings us to an intriguing observation: the role of salts. Enhanced corrosion is often noticeable on vehicles in areas where roads are heavily salted during winter. Just as a salt bridge completes the electrical circuit in a voltaic cell, the ions from the salt act as an electrolyte, facilitating the completion of an electrical pathway. Now, isn't that fascinating? Let's move forward and explore more captivating aspects of chemical reactions and their effects. Hello, dear students. Today's topic is all about protecting iron objects from a natural process known as corrosion. We'll explore how various methods can shield iron surfaces and prevent them from deteriorating over time due to exposure to oxygen and water. Let's dive into the details. Welcome back, everyone. As we discussed earlier, one effective method to prevent corrosion is by coating iron objects with materials like paint or other metals. This layer acts as a barrier, preventing direct contact between the iron surface, oxygen, and water. The objective here is to safeguard the iron structure and appearance. Remember, maintaining a seamless coating coverage is crucial to ensure a long-lasting protection. Great to have you back, students. Now, let's delve into what happens when the protective coating is damaged. Once the coating is breached, oxygen and water can come into contact with the iron surface. This contact triggers a chemical reaction known as oxidation. During this process, iron atoms lose electrons and transform into iron ions. This phenomenon gradually weakens the iron object. Hello again, students. Now, let's talk about a remarkable solution to combat corrosion: galvanized iron. Galvanized iron is simply iron covered with a thin layer of zinc. What makes this combination so effective? Well, it's due to the difference in their reduction potentials. The reduction potential of zinc, standard electrode potential, is more negative compared to that of iron. This means that when exposed to oxygen and water, zinc gets oxidized more readily than iron. As a result, even if the zinc coating is damaged, it acts sacrificially by corroding instead of the iron itself. Welcome to the final topic of today's lesson, my attentive learners. Let's uncover the inner workings of galvanized iron. In this setup, zinc becomes the anode, willingly undergoing oxidation by losing electrons. On the other hand, iron takes on the role of the cathode, where oxygen reduction takes place. This intricate dance of reactions ensures that the iron object remains safe from corrosion, even if the zinc coating suffers a break. Remember, students, these mechanisms play a vital role in preserving various iron objects around us. Null. Alright, my bright students, let's dig deeper into the practical application of cathodic protection. Consider underground pipelines and storage tanks made of iron. These structures are often susceptible to corrosion. But fear not, for we have a solution. By setting up a voltaic cell, we make the iron structures the cathode. This means they're shielded from corrosion. How does this work, you ask? Well, we introduce pieces of a metal that's more readily oxidized than iron, like magnesium with a redox potential of -2.37 volts. These magnesium pieces, buried near the pipeline or tank, are connected by wires. In moist soil prone to corrosion, the sacrificial metal, magnesium in this case, becomes the anode, undergoing oxidation to protect the iron cathode. It's like a shield for our structures. Let's explore the environmental factor that plays a vital role in cathodic protection. Moist soil is a notorious culprit when it comes to corrosion. In such environments, metals are at risk of degrading due to chemical reactions. This is where our trusty sacrificial anode steps in. Buried in the moist soil, it becomes the target of oxidation, ensuring that the iron cathode remains unharmed. The concept of cathodic protection is truly a marvel, offering a powerful defense mechanism against the damaging effects of corrosion. As we wrap up our exploration of cathodic protection, let's highlight the remarkable benefits it brings to our infrastructure. Imagine the longevity of our metal structures, free from the clutches of corrosion. This not only ensures the durability of pipelines and tanks but also has significant economic and safety implications. The technique finds its application in diverse scenarios beyond underground pipelines, showcasing its wide-ranging impact. Remember, students, as we learn about these scientific marvels, we're empowering ourselves with the knowledge that drives progress and innovation in our world. Welcome back, dear students. Today, we're delving into an essential topic: corrosion and the intriguing anode-cathode reactions that accompany it. Let's start with the corrosion of iron metal. When iron is exposed to the environment, it can undergo a chemical reaction with substances like water and oxygen. This reaction leads to the formation of aqueous iron, ions. But what's truly fascinating is how this process occurs at the molecular level. The corrosion process involves two primary reactions, the anode reaction and the cathode reaction. The anode reaction involves the oxidation of iron atoms, which lose electrons and become ions. On the other hand, the cathode reaction involves a reduction process, where another substance gains those lost electrons. This interplay of reactions results in the corrosion of iron. Now, let's explore another intriguing example. Hello again, students. Let's continue our journey by exploring the air oxidation of Fe2+ to form Fe2O3, which is commonly known as rust. This transformation involves some captivating chemistry. As Fe2+ ions react with oxygen from the air, they undergo oxidation, resulting in the formation of iron oxide, Fe2O3 and water. To fully grasp this process, we break it down into balanced half reactions. On one hand, Fe2+ ions lose electrons in the anode reaction, becoming ions. On the other hand, oxygen molecules from the air gain those electrons in the cathode reaction, forming water molecules. Together, these reactions create a complex interplay of electron transfers and chemical transformations. Now, let's explore the interaction between tin and iron. Great job following along, students. Now, let's discuss a practical application that helps protect iron from corrosion. Have you ever wondered how some objects manage to stay corrosion-free? One technique is coating iron objects with a layer of tin. This coating serves as a shield against corrosion, and it works through a mechanism known as cathodic protection. In this process, the tin coating acts as a cathode, attracting any potential oxidation reactions that might occur on the iron surface. This effectively prevents the iron from undergoing oxidation and corrosion. The tin coating essentially takes one for the team and safeguards the iron underneath. It's an impressive example of how understanding chemical reactions can lead to real-world solutions. Let's keep the momentum going. Welcome back, students. Today, we're delving into the fascinating world of copper oxidation states in different oxide compounds. Let's begin with cuprous oxide, denoted as CuO. In this compound, copper takes on an oxidation state of +1. Moving on to cupric oxide, with the formula CuO, we find copper in an oxidation state of +2. Now, things get even more interesting as we explore some less common compounds. Copper peroxide, a compound formed from elemental copper's reaction with oxygen, carries a suggested formula of CuO. In this compound, we can envision a more complex arrangement of copper and oxygen atoms. Lastly, we encounter the intriguing copper oxide. While less common, its potential chemical formula is suggested as CuO. This compound showcases copper in a +3 oxidation state, demonstrating the diverse ways copper can interact with oxygen. Keep in mind that these oxidation states play a crucial role in determining the properties and behavior of these compounds. Now, let's journey deeper into the world of copper's oxidation states and their implications. Good day, students. Today, we're diving into the intriguing realm of electroplating and non-spontaneous redox reactions. Our exploration takes us into the world of materials and their unique properties. Imagine the fusion of structural strength with decorative appeal or corrosion resistance. An excellent example is the chrome plating on iron, which results in a highly resilient and shiny surface. Another fascinating instance is gold plating onto copper, commonly employed in connectors for the electronics industry. Additionally, the combination of silver plating onto a copper-nickel-zinc alloy serves decorative purposes, enhancing the appearance. But how do these transformations occur? Well, they involve a process driven by electrical current, where non-spontaneous reactions take place. These reactions may not occur naturally but can be induced using electrical energy. The same principle applies to the extraction of certain metals from their ores. As we journey through this section, You'll not only comprehend the reactions within an electrolytic cell but also appreciate the concept of non-spontaneous redox reactions and the vital role of electrical energy in driving them. Welcome back, dear students. Let's delve deeper into the world of cells, not the biological kind, but rather, voltaic and electrolytic cells. These cells play a pivotal role in harnessing energy and driving reactions. Voltaic cells are our starting point, fueled by spontaneous redox reactions. These reactions occur naturally, releasing energy that can be harnessed for various purposes. Picture it like a self-sustaining power source. On the other hand, we have electrolytic cells. These cells, unlike their voltaic counterparts, deal with non-spontaneous reactions. What makes them special is their ability to use electrical energy to make these reactions occur. It's like giving a little push to start something that wouldn't happen on its own. To grasp this concept, envision the difference between a self-propelling machine and one that needs an external force to set it in motion. As we journey through these fascinating cell types, you'll uncover the magic of harnessing energy and making chemical transformations possible through clever use of electricity. Hello again, students. Today, we're exploring the myriad applications and extractions driven by electroplating and electrical energy. Think about the items around you that possess both striking looks and functional benefits. This enchanting combination is often achieved through electroplating, where metals like chrome, gold, or silver are coated onto other materials. This process not only enhances aesthetics but also bestows functional advantages like corrosion resistance. Imagine those stylish faucets or shiny jewelry. They owe their allure to the wonders of electroplating. Furthermore, the realm of extraction unfolds before us. Electrical energy becomes our ally in extracting metals from their ores. The same principle that operates within electrolytic cells is harnessed on a larger scale to obtain pure metals from naturally occurring compounds. We're essentially unlocking the potential hidden within Earth's resources. So, remember, as you observe the world around you, the fusion of materials and the magic of electricity work hand in hand to shape our surroundings in fascinating ways. Hello again, students. Today, we're delving into the fascinating world of electrolysis and the role of electrical energy in driving chemical reactions. Imagine a scenario where electricity is used to break down molten sodium chloride into its individual elements, sodium, Na, and chlorine gas, Cl2. This process, known as electrolysis, is achieved through electrolytic cells. These cells consist of two electrodes submerged in either molten salt or a solution. A battery or another electrical energy source acts like an electron pump, pushing electrons into one electrode and pulling them from the other. Just like in our previous discussions about voltaic cells, the electrode where reduction occurs is termed the cathode, while the electrode where oxidation happens is called the anode. Let's take a closer look at the electrode reactions that occur during the electrolysis process. At the cathode, reduction takes place. In the case of molten NaCl, Na ions receive electrons and undergo reduction, leading to the formation of sodium. This process ensures that sodium ions near the cathode continue to migrate, sustaining the reaction. On the other hand, at the anode, oxidation is the key process. Cl ions move toward the anode and undergo oxidation, forming chlorine gas, chlorine. The overall result of these reactions is the decomposition of molten NaCl into sodium and chlorine gas. Now, let's piece together the puzzle of the overall electrolysis reaction. By combining the cathode and anode reactions we discussed earlier, we arrive at a comprehensive understanding. During the electrolysis of molten natrium chloride, the combined reactions result in the transformation of Na plus ions and Cl minus ions into sodium atoms and one chlorine molecule. This process highlights the remarkable ability of electrical energy to drive chemical transformations, showcasing the power of science and technology. Let's wrap up our exploration of electrolysis by considering its practical applications. Electrolysis isn't just a fascinating concept, it has real-world applications. Through electrolysis, we can produce a wide range of substances, including hydrogen gas and aluminum. This process allows us to harness electrical energy to manipulate chemical reactions, shaping materials and technologies that impact our lives in numerous ways. As we conclude today's lesson, remember the fundamental role that electrical energy plays in driving these reactions and opening the door to exciting possibilities. Welcome, dear students, to the intriguing world of electrochemistry and the phenomenon of electrolysis. Today, we're going to delve into the fascinating realm of energy transfer through electrodes and the wonders it brings forth. Figure 20.28 catches our attention, showcasing how an energy source is intricately connected to the electrodes. Here, the positive terminal links with the anode, while the negative terminal connects to the cathode. The outcome? Electrons are compelled to journey from the anode to the cathode, marking a captivating dance of charge carriers. Now, let's move on and ponder an interesting question. Do we obtain the same results when we perform electrolysis on an aqueous solution of a salt, as opposed to a molten salt? Surprisingly, the answer is often no. The high melting points of ionic substances lead molten salt electrolysis to demand intense heat. But when it comes to aqueous solutions, water itself can be a contender, getting oxidized to oxygen or reduced to hydrogen instead of the ions in the salt. As we explore the electrolysis of sodium chloride, notice that the electrodes remain inert. They serve as mere platforms for the captivating interplay of oxidation and reduction. However, electrochemistry doesn't stop there. Practical applications abound, including the mesmerizing art of electroplating. This process uses electrolysis to coat one metal with a thin layer of another, enhancing its appearance or bestowing upon it the power to resist corrosion. Picture this: steel receiving a delicate layer of nickel or chromium, or a less expensive metal adorned with a precious coat of silver. Figure 20.29 takes us further into this world, revealing an electrolytic cell for the enchanting process of nickel electroplating onto a piece of steel. Stay curious, for our exploration of electrochemistry has only just begun. Hello, young minds. Today's lesson takes us into the world of electrochemical cells, where fascinating reactions unfold. Our electrochemical journey begins with an understanding of the cell components. We have an anode, which is a strip of nickel metal, and a cathode, composed of steel. These electrodes find their place within a solution of NiSO, AQ, which adds another layer of complexity to our exploration. As we continue, we'll see the role of external voltage in driving reactions. Now, let's move on to understanding the intriguing process of reduction that occurs at the cathode. Greetings, inquisitive minds. As we focus our attention on the cathode, we uncover a captivating process known as reduction. When an external voltage is applied, something remarkable happens at the cathode. Let's delve into the world of standard reduction potential. Ni2+, the ion derived from nickel, boasts a reduction potential of -0.28 volts, a value that holds significance in comparison to another player in this story, H2O, with a reduction potential of -0.83 volts. As fate would have it, Ni2+ emerges as the preferred candidate for reduction due to its less negative potential. This preference leads to the enchanting outcome of depositing a layer of nickel metal onto the steel cathode. Ahoy, brilliant learners! As we wrap our minds around the cathode reduction process, it's time to grasp its real-world significance. The deposition of a nickel metal layer is no mere coincidence, it holds practical value. This layer serves as armor, providing enhanced protection to the cathode. Imagine the possibilities for various applications that rely on this enhanced durability. Additionally, this process finds a special place in the world of electroplating. Through cathode reduction, electroplating processes allow us to coat objects with a layer of nickel, enhancing their appearance and properties. And there you have it, an insightful journey into the realm of electrochemical reactions and cathode magic. Bravo, attentive learners! Before we conclude, let's briefly revisit our adventure. We uncovered the roles of anode and cathode within an electrochemical cell. Observing how the reduction of Ni2+ ions takes center stage at the cathode. The preference for Ni2+ over H2O was an enlightening discovery, leading to the formation of a nickel metal layer on the steel cathode. And what's even more exciting, this process finds its place in practical applications, contributing to cathode protection and electroplating marvels. As we bid adieu to today's lesson, keep this knowledge close, it's a stepping stone to unlocking even more mysteries in the world of chemistry and energy transformations. Until next time, curious minds. Hello, students. Today, we're delving into the intriguing world of electrochemical cells and the fascinating behavior of nickel in these systems. Let's start by discussing the process that takes place at the anode. The anode is where the nickel metal undergoes oxidation. To understand this phenomenon, we need to examine the substances in contact with the anode, H2O and NiSO4, Aq2, compared to the anode material, Ni. Interestingly, Ni2+ and SO4 ions in the solution cannot be oxidized, as they already exist in their highest oxidation state. However, both H2O solvent and the Ni atoms in the anode can indeed undergo oxidation. The equation 2H2O, L, right-pointing arrow O2, G, plus 4H plus, Aq, plus 4E with a standard reduction potential of plus 1.23 volts demonstrates this process. On the other hand, Ni's right-pointing arrow Ni2 plus, Aq, plus 2E with E degree red equals minus 0.28 volts. As we've learned, the half reaction with the more negative E degree red value tends to undergo oxidation more readily. In this case, Nis is oxidized at the anode rather than H2O. But hold on, even though it might seem like nothing significant is happening overall, there's more to the story. The transfer of Ni atoms from the anode to the cathode occurs, leading to the deposition of a thin layer of nickel on the steel cathode. The standard EMF for the entire reaction is calculated using the difference between the reduction potentials of the cathode and anode, resulting in an EMF of 0. This means that a small external EMF is sufficient to drive the transfer of nickel atoms between the two electrodes. Let's continue our exploration of electrochemical processes and the intriguing world of reactions. Good day, students. Today, we're delving into the fascinating world of quantitative aspects of electrolysis. This journey takes us through the stoichiometry of half reactions and the crucial role electrons play in electrolytic processes. Imagine, as we explore, that we're uncovering the secrets of how matter transforms through the exchange of electrons. Our journey begins with a classic example: the reduction of sodium ions, Na+, to sodium, Na. This process involves a one-electron transfer. Yes, you heard it right. A single electron is all it takes to transform sodium ions into solid sodium. This simple equation, Na++ E right-pointing arrow Na, reveals that 1 mole of electrons causes the deposition of 1 mole of Na metal. But wait, there's more. Let's move on to our next example to truly grasp the concept. Welcome back, eager learners. Our exploration continues with a dive into the world of copper transformation. Ever wondered how copper ions, Q2+, turn into pure copper, Q? This transformation requires the exchange of 2 electrons per copper ion. This equation, Q2++ 2 E right-pointing arrow Q, shows us that for every mole of Cu2+ ions, 2 moles of electrons are needed to produce 1 mole of solid copper. Imagine the intricate dance of electrons leading to the formation of a metal that has played a pivotal role in our history. As we peel back the layers of science, let's now move on to our next example, where electrons shape the transformation of a different element. Marvelous minds. Let's continue our exhilarating journey into the world of electrolysis. Our next stop brings us to the electrifying transformation of aluminum ions, into aluminum. Brace yourselves for this captivating change. To achieve this remarkable feat, 3 electrons are required for each aluminum ion. This equation, aluminum ions plus 3 electrons right pointing arrow aluminum, illustrates that a triumphant trio of electrons brings forth 1 mole of aluminum from each mole of aluminum ions. The sheer intricacy of these processes, driven by the exchange of electrons, showcases the elegance of nature's dance. With these concepts firmly grasped, let's move forward and explore more electrifying examples. Welcome back, students. Today, we're delving into the intriguing world of electrolytic cells and the captivating relationship between the amount of substance transformed and the electrons involved. Imagine a scenario where we have a half reaction occurring within an electrolytic cell. In this scenario, the quantity of substance reduced or oxidized is directly linked to the number of electrons that enter the cell. Now, let's talk about something known as charge. In electrical circuits, like those found in electrolytic cells, charge is measured in coulombs. Did you know that the charge on 1 mole of electrons is an astounding 96,485 coulombs? That's quite a charge. Speaking of which, a coulomb is defined as the amount of charge passing a point in a circuit in 1 second when the current is 1 ampere. In other words, it's like the currency of electrical charge. So, how do we calculate the number of coulombs passing through a cell? Simple. Just multiply the current in amperes by the elapsed time in seconds. Coulombs equal amperes times seconds. Our visual aid, figure 20.30, gives us a clear picture of how substances transform and connect to the quantity of electrical charge used in electrolysis. Keep in mind that these relationships are also applicable in voltaic cells. Remember, electrons play a crucial role in electrolysis reactions, almost like reagents, guiding the transformation of substances. Let's move on and explore further. Hello, dear students. Today's lesson takes us into the fascinating realm of electrometallurgy and electrolysis. Let's embark on a journey to understand the processes involved in producing and refining metals. The various techniques used in this field collectively fall under the term electrometallurgy. We'll explore how these methods can be categorized based on whether they utilize electrolysis of molten salts or aqueous solutions. But what exactly sets these two approaches apart? Let's delve deeper. Welcome back, eager learners. In our electrifying exploration of electrometallurgy, let's focus on electrolytic methods involving molten salts and their connection to active metals. Active metals like sodium, magnesium, and aluminum are in the spotlight here. We've learned that obtaining these metals from aqueous solutions poses challenges, due to the ease of water reduction compared to metal ion reduction. This intriguing phenomenon is connected to the standard reduction potentials of these elements. Let's visualize this with a concrete example. Greetings, inquisitive minds. As we journey further, let's uncover the significance of standard reduction potentials in electrometallurgy. The potential for reduction varies among different substances, and this affects the ease of electrolysis. In our context, the reduction potentials of water and active metal ions play a pivotal role. We encounter a historical challenge when it comes to producing aluminum metal. This remarkable metal is derived from bauxite ore, which undergoes chemical treatment to concentrate aluminum oxide. However, the melting point of aluminum oxide poses an obstacle, making it unsuitable for use as a molten medium for electrolysis. Bravo, attentive scholars! In our final stretch, let's explore the ingenious solutions employed to overcome the high melting point challenge associated with aluminum oxide. Innovations in technology have paved the way for us to tackle this obstacle effectively. As we wrap up our enlightening journey into electrometallurgy and electrolysis, take a moment to reflect on the interplay between reduction potentials and the feasibility of electrolysis processes. Our quest to harness metals through these fascinating methods showcases the dynamic relationship between chemistry and industry. Keep your curiosity alive, for the world of science is an endless adventure. Welcome, dear students. Today, we're embarking on a fascinating journey into the world of aluminum production. Our focus will be on the innovative Hall-Héroult process, which holds its name from the brilliant minds behind its creation, Charles M. Hall and Paul Héroult. In the late 19th century, Hall took up the challenge of finding an efficient method to extract aluminum. This endeavor arose from the complexities of reducing highly reactive metal ores. At that time, the prevailing method involved costly chemical reductions using sodium or potassium. Can you believe that? Back in 1852, aluminum was even more expensive than gold? But everything changed with the advent of the Hall-Héroult process. Let's delve into the intricacies of this revolutionary technique and how it transformed the aluminum industry. As we dive deeper into the Hall-Héroult process, it's important to understand the challenges that led to its development. In the past, obtaining aluminum was a costly endeavor. Traditional methods involved chemical reductions using sodium or potassium, which were expensive processes. To put things into perspective, the cost of aluminum was once even higher than that of gold. Imagine the hurdles that had to be overcome to make aluminum more accessible. The Hall-Héroult process emerged as a groundbreaking solution to these challenges, and we're about to discover how it changed the course of aluminum production. Let's take a closer look at the brilliant mind behind the Hall-Héroult process, Charles M. Hall. Around 1885, Hall embarked on a journey to find a more efficient way to extract aluminum. Inspired by the challenges posed by reducing highly reactive metal ores, Hall began to explore the realm of electrolytic processes. His goal was clear: to develop a method that could reduce aluminum from its ores without the exorbitant costs associated with earlier methods. Through his dedication and innovative thinking, Hall set the stage for a revolutionary breakthrough in aluminum production. Our story takes an exciting turn as Charles M. Hall's path intersects with another brilliant mind, Paul Héroult. Together, they collaborated to develop the electrolytic process that would change the world of aluminum production. This process involved using electricity to extract aluminum from its ores efficiently. The commercial viability of aluminum production soared, making this metal more accessible to various industries. The Hall-Héroult process not only revolutionized aluminum manufacturing but also had a profound impact on technological advancements. Stay tuned as we unravel more about this incredible journey. Now, let's delve into the heart of the matter, the Hall-Héroult process itself. This ingenious technique involves using electricity to extract aluminum from its primary source, alumina. Through electrolysis, aluminum oxide, alumina, is broken down into its components, aluminum and oxygen. The beauty of this process lies not only in its efficiency but also in its contribution to energy conservation. The Hall-Héroult process marked a turning point in the aluminum industry by providing an energy-efficient method to produce this valuable metal. As we wrap up our exploration, remember the remarkable journey of innovation and collaboration that led to the transformation of aluminum production.